day, students. Today we are going to continue our lesson from where we stopped the last time we met. We were talking about chemical combination, and in the last lessons we handled covalent bonding and ionic bonding. I did tell you from the beginning of the introduction of that lesson that there are four basic types of chemical bonding. We have the covalent bonding, the ionic bonding, the coordinate covalent, or what we call dative bonding, and then metallic bonding. So we have handled the first two. Today we'll be talking about coordinate covalent, or what we call dative bonding. Now I've put up the definition here. I say coordinate covalent or dative bonding involves sharing of electrons, but the shared pair of electrons is contributed by only one of the participating atoms. Remember, in covalent bonding, we say that covalent bonding involves sharing, but in covalent bonding, the pair of electrons to be shared are contributed equally by the participating atoms. But in coordinate covalent bonding, only one of the participants contributes the pair of electrons to be shared. So that is the difference between coordinate covalent bonding and then an ordinary covalent bonding. Then we say coordinate covalent bonding or dative bonding occurs between an atom that has a lone pair of electrons in the outer shell and another atom that has an empty valence orbital, and therefore requires one pair of electrons to complete an octet or a duplet. What do we mean by this? Say for a coordinate covalent bonding to occur, there must be what we call a lone pair of electrons. That means a pair of electrons that is not being shared. Okay, an atom that has a pair of electrons that is not being shared in the bonding it is presently in, that kind of pair of electrons we call a lone pair. If I may take a little example and explain what I mean, like for nitrogen. Nitrogen is in group 5. It has 5 electrons in its outer shell. Nitrogen has 5 electrons in its outer shell, and therefore it needs 3 more electrons to complete an octet. That means to have a complete 8 electrons in its outer shell. And if it is about to form ammonia, it bonds with 3 atoms of hydrogen. One hydrogen will come here. Remember what we learned in covalent bonding? Another hydrogen will come here. Another hydrogen will come here. So that you will now form N. There's a bond with hydrogen here, there's a bond with hydrogen here, there's a bond with hydrogen here. Then this pair of electron is not being used. It's still here. That is what we call a lone pair of electrons. It's a pair of electrons that is not being shared between nitrogen and hydrogen. So, if you have molecules that have this kind of lone pair of electrons, then they can participate in coordinate, covalent, or dative bonding. Alright? So, and then that is one. Then the other atom will now be, the other participant will have an empty, or it has, what I say here, it has an empty valence orbital, and therefore needs a pair of electrons to complete it. Like hydrogen. Hydrogen ordinarily, in its atomic form like this, hydrogen has 1 electron and needs 1 more electron to complete its 1s orbital, which is the only shell it has. So if hydrogen loses electron to become hydrogen ion like this hydrogen ion now does have a vacant orbital. It does not contain any electron because originally it has 1 electron. Now it has lost 1 electron to become hydrogen ion, so it does not have any electron at all. So when this kind of ion that needs 2 electrons to complete its outer shell, and then it comes across something like ammonia that has a lone pair of electrons that is not being used to share with this other hydrogen, then this one can accommodate this hydrogen, and then they can share this electron. So that's what we mean by an atom having a lone pair and another one having an empty valence orbital. Okay, the atom that contributes the pair of electrons to be shared is called the donor atom. In this case, like this hydrogen now that has a lone pair of electrons is what we call a donor atom. While the other atom is the acceptor atom. Hydrogen ion now becomes the acceptor atom.
You see, the problem is you cannot be reading. Wait, let me show you something.
Good day, students. Today we'll be continuing our lessons from where we stopped the last time we met. Okay, I introduced chemical combination. And I did say that there are 4 types of chemical bonding: the covalent bonding, the ionic bonding, the coordinate covalent bonding, or what we call dative bonding, and then the metallic bonding. And the last time we were in class, we had discussed covalent bonding and ionic bonding. Today, I'll be talking about coordinate covalent, or what we call dative bonding. I've put up the definition here on board. I said coordinate covalent or dative bonding involves sharing of electrons. This is electrons, sharing of electrons. But the shared pair of electrons is contributed by only one of the participating atoms. You remember in covalent bonding, we say the shared pair of electrons is contributed equally by the participating atom. If they are sharing one pair, which is 2 electrons, it means the other atom will bring 1, the other atom will bring 1, and then they will share the pair. If they are going to be sharing 4 pairs, that means they will have double covalent bonding. The other one will bring 2, the other one will bring 2, and then they share the 2 pairs of electrons. But in coordinate covalent bonding, only one of the participants contributes the shared pair that are going to share. They are going to share together. Okay. So coordinate covalent or dative bonding occurs between an atom that has a lone pair of electrons in the outer shell and another atom that has an empty valence orbital, and therefore requires one pair of electrons to complete an octet or a duplet. You remember we said last time that the reason why atoms go into chemical combination is so that they can have an octet configuration or a duplet. Octet, that means to have 8 electrons in the outer shell, or a duplet to have 2 electrons in the outer shell, like helium, hydrogen, lithium. Those ones, they have 2 electrons in the outer shell, which is, because they have only a single shell, as for hydrogen and helium. Alright, so what do we mean by a lone pair of electrons? If I will quickly do a little explanation here to see what we mean by a lone pair of electrons. Like nitrogen, you know nitrogen is group 5. And group 5 elements have what? 5 electrons in their outer shell. 5 electrons in their outer shell. Okay? If nitrogen is combining with hydrogen to form ammonia, that means 1 nitrogen and 3 hydrogen. Then what happens is 1 hydrogen will come here with this electron, the other one will come here and share this one, another will come here and share this one, so that it can give you the ammonia molecule. Now if you observe, you will see that this one, they are shared. This one is shared. This one is shared. But this one is also a pair of electrons, but it's not being shared. Okay, it's only nitrogen that has it. So this one we call it a lone pair. That's what we call a lone pair of electron. So if an atom that has this type of lone pair of electron comes across an atom or an ion like hydrogen. Hydrogen ordinarily like this has one atom, one electron in its one and only shell. And it needs one more electron to complete that one shell so they can have a duplex configuration. But if this hydrogen now loses electron to become hydrogen ion, it means it does not have any electron left. That means it should be looking for 2 electrons before it can have 2 electrons in its one and only shell. It will need 2 electrons. But it does not have any to contribute. It just has an empty outer shell. Okay? So if you come across an atom like nitrogen that has a lone pair of electrons, then the nitrogen will be able to accommodate this hydrogen. It will come with its empty shell, and then it will share in this lone pair of electrons. So that is how coordinate covalent bonding is being formed. And I say the atom that contributes the pair of electrons to be shared is called the donor atom. In this case, nitrogen is our donor atom, while the other atom is the acceptor atom. In this case, the hydrogen ion becomes our acceptor atom. Okay? An arrow, okay, represents the bond formed from the donor to the acceptor. So coordinate covalent bonding is usually indicated by an arrow, like in this case now. This one now, we'll put an arrow here to show that this is where the coordinate covalent bonding is. And the electrons, the one that is donating the electron is nitrogen. So from nitrogen to the hydrogen ion. Okay, so you represent that by an arrow. Okay, example of molecules that possess lone pair of electrons are ammonia and water. They are not the only ones, but these are the typical example. We have ammonia, NH3, and water molecule H2O. They are the ones, the most common example of molecules that possess what we call a lone pair of electrons. So now let's take a look at some examples of coordinate covalent bonding. Okay, the first one we have here is the formation of ammonium ion, that is NH4+. Okay, the ammonium ion is formed between nitrogen and hydrogen ion. Ammonia and hydrogen ion. So the lone pair of electrons in the valence shell of nitrogen atom in ammonia is donated for sharing with the empty 1s. This is 1 as number 1. The empty 1s orbital of hydrogen ion. Okay? So, as I explained earlier, this is ammonia. Okay? Nitrogen has 5 electrons in its outer shell. It's using 1 to bond with hydrogen now. It's contributing 1 to form this covalent bond. It's also contributing 1 to form this covalent bond. So it has this lone pair of electrons. So if it comes across hydrogen ion that has empty shell and is looking for a pair of electrons, it will be able to share it with this hydrogen ion, thereby forming what we call a coordinate covalent bonding. Now, which one is the coordinate covalent bonding here? This one. Okay? If you are able to see that, that means you are following, because it's indicated by an arrow. Okay? So this one you'll be able to know. From seeing this, you know that it is nitrogen that is contributing. Hydrogen is not bringing anything, because the arrow goes from nitrogen to hydrogen. Okay? And then you enclose it in a square bracket and a plus sign. Remember, the hydrogen is coming with a positive sign here. So the positive sign is what we are putting here. Or what we normally see is written NH4+. So that is one example of coordinate covalent bonding. The second example we are going to see is the formation of hydrosonium ion. That's H3O+. That's hydrosonium ion. Here, one of the lone pair of electrons in the valence shell of oxygen atom in water is donated for sharing with the empty 1s orbital of hydrogen ion. Oxygen, if you write the electron configuration of oxygen, you find that it has 6 electrons in its outer shell. Okay, and it is in group 6. Here it is using 1 to share with hydrogen here, using 1 here to share with hydrogen in the formation of water. So you will see that for water, this oxygen has 2 lone pair of electrons. There are 2 pair of electrons that are not being used in the formation of water here. So if it comes across an hydrogen ion, it will be able to use one of the lone pair, okay, one of the lone pair to share with this hydrogen ion, thereby forming a coordinate covalent bond. Once again, this is our coordinate covalent bond, and that gives you hydrosonium ion. Okay, as I said, these are not the only example. One of the typical examples that we see is formation of complex ion. I'm sure you must have heard of complex ion. So, coordinate covalent bonding is what is involved in formation of a complex ion. A typical example is the complex ion formed between copper 2 ion and ammonia. If by the time you go to the lab and then your teacher is teaching you qualitative analysis, test for copper 2 ion, you know, we add excess ammonia, okay, and then we get deep blue solution. The formation of that deep blue solution is due to the formation of the complex ion. All right, let's go on to see metallic bonding. That's what we will say about coordinate covalent bonding. Let's talk about metallic bonding now. Okay, before we start talking about metallic bonding, let's quickly talk about the physical properties of the coordinate covalent bonding. Okay, you can see I did not list any properties here. They have the same property with covalent, normal covalent bonding. Okay, once the coordinate covalent bonding is formed, it behaves just like a normal covalent compound. Okay, so those properties I gave you for covalent compounds is the same properties you will consider for coordinate covalent compounds. Okay, now before we still go to the metallic bonding, I want to talk about ammonium fluoride. Ammonium fluoride is a very unique compound in the sense that it has 3 bondings in it. Remember, the formula of ammonium fluoride is NH4Cl. In this compound, we have covalent bonding. We have covalent bonding. We have coordinate covalent bonding, and then we have ionic bonding. This compound possesses all these 3 compounds. I mean, the types of bonding, like the formation of ammonia. Okay, nitrogen plus hydrogen to give you ammonia, or let me just write it the way we know. 1 nitrogen combined with 3 hydrogen to give you this NH3. You know, we say the bonding between them is hydrogen here, hydrogen here, hydrogen here. Okay, all these ones are covalent bonding. So to form ammonia is covalent bonding. The reaction between ammonia and hydrogen ion to form ammonium ion. Okay, this one is what we just learned now. That is what coordinates covalent bonding. Then the reaction between the ammonium ion, that's the NH4+, plus the chloride ion to give you NH4Cl is ionic. You know, we say ionic has to do with positive ion and negative ion. You know, electrostatic force holding the molecule together. So this crystal of ammonium chloride is finally formed by ionic bonding. So you can see that in this one molecule or one compound of ammonium chloride, you have covalent bond, you have coordinate covalent bond, and you have ionic bonding. Okay, so I felt I should mention that before we go to metallic bonding. Now let's talk about metallic bonding proper. Metallic bonding is the bonding that is formed between metals. Okay, any metal you see, what is holding those metal atoms together is what we call metallic bonding. Okay, and I say that the valence electrons in metals are not localized, they are mobile. Okay, like metals of 1, sodium, all of them have 1 electron in their outer shell. Okay, so when you have a lot of atoms of sodium, atoms of sodium, atoms of sodium, atoms of sodium, these ones, each of them will now have the electrons, the valence electrons, the outer electrons all there. Okay, if you go like in calcium, okay, calcium that is in group 2, which means each of them now will now have 2 electrons in its outer shell, 2 electrons in the outer shell, 2 electrons in the outer shell, 2 electrons in the outer shell. And we say these valence electrons are not localized, that means they are not static in one place. They are mobile, they move about. So these ones will be moving about, moving in between these atoms, they will just be moving. And they form what we call a cloud or a sea of electrons. You know, there's a pool of electrons that they form. And you know, we learn when we're talking about, when we're treating structure of the atom. We say that the electrons are negatively charged. And inside the nucleus of the atom, you have protons and neutrons. Protons are positively charged, the neutrons are neutral. So the nucleus of the atom is positively charged, while these electrons are negatively charged. That means this cloud of electrons will be pulled, there will be attraction, there will be a force of attraction that is pulling it towards the nucleus. Okay? That's why we say the electrostatic force of attraction between the positive nuclei, that means the nucleus that has a positive charge, and then the cloud of electrons, which is negatively charged, is called metallic bond. So when we talk about metallic bond, is the force of attraction between the cloud of electrons that are negatively charged and then the positively charged nuclei of the metallic atom. That is what causes, what brings about, or what is responsible for metallic bond. Alright? Now let's quickly look at the physical properties of metals. We say metals are good conductors of heat and electricity. I am sure you have learned this even from your junior class, the properties of metals. They are good conductors of heat and electricity. And what's the reason why they are able to conduct heat and electricity? Still, the reason is because of the mobile valence electrons that they have. Once you connect electric current from one end there, the mobile electrons, because they are free to move, they will carry the electric current from one end of that conductor to the other. They will be carrying, as they move, they will carry the electric current along. That's why you say they conduct electricity. Even the heat is the same thing. The mobile electrons are what they are the things that carry the heat across one end to the other. Then we say they are able to conduct heat. So metals are good conductors of heat and electricity. And I say the reason is because they have mobile electrons. They are ductile and malleable. You can easily heat them into shape, you bend them, and you stretch them. Very easy to do that. And the reason is still because they have these mobile electrons. They have high melting points. Okay, the high melting point is because of the nature of the bonding that is formed between them. They give them high melting point. We say they also have high tensile strength. In your physics, I'm sure your physics teacher will explain that one to you much more. Okay, they exhibit bright metallic luster. That means they are shining. You know, some metals and they shine. That's what we call metallic luster. That's shining nature of them. Okay, then they form cations. Okay, with ease. This is one property of metals. Metals don't form negative ion. You don't see a metal, maybe X, with a negative charge. Metals don't form, this is anion. Metals don't form anion. They don't form ion with negative charge. Anywhere you see a metal, you will see that it carries a positive charge. Okay? Depending on the number of electrons it is losing, it could be maybe 2 plus, could be 3 plus. This X, Y, and Z are just assuming that they are representing, standing for the elements. Okay? So, they form cations. These are what we call cations. They give out electrons. And then, the ease with which an element or a metal gives out this electron determines its reactivity. So that's why you don't see that. If you look at the periodic table, okay, we say as you go down the group, ionization energy decreases. That means the ease with which you remove electron from the outer shell of the atom becomes easier as you go down the group. So we will be correct to say that reactivity for metals increase as you go down the group. Okay, because their reactivity has to do with the ease with which they give out electrons. So with this, we come to the end of our lesson. Okay, let's quickly take this assignment. This assignment on the board. 5 assignments. I hope you'll be able to read. This one's was running short of space, so I had to squeeze them. Do these assignments and then send it on my WhatsApp. Maybe for the sake of some of you who are just joining the class for the first time, you will not have my WhatsApp number. It is 07034639492. So you do this assignment and you send it to my WhatsApp. I will see you in the next class.